Okay, so let's take a look at this transformer. Raise your hand if you've ever heard of the transformer before besides this class. Heard of it prior to coming into here? Okay, I'm not talking about the machines that change from a car to a robot, sort of that. That's what your thought is about. Transformers are critical to our electrical infrastructure. It is a device that's for increasing or decreasing an AC voltage. Now, transformers only work with AC. They do not work with DC. The main reason why Tesla won the current wars is because of the transformer. Because you can take an AC voltage and you can change its value. You cannot do that with a DC using this kind of device. So a transformer, and I have a mock-up for you. I'll show you how that works. But essentially, it consists of a laminated iron core, and it's got multiple turns around one side called the primary, the other side called the secondary. So the primary and secondary side of a transformer allows us to transform voltage from one side to the other. Consists of two coils of wire known as primary and secondary coil, laminated iron core around which are wrapped to coils, or the coils are interwoven. So usually you'll see them drawn like this, but if you were to break apart a transformer, you'd probably see them interwoven in many cases. When an AC voltage is applied to the primary, the changing magnetic field it produces, and I want to talk about the changing magnetic field. On this side over here, we have a coil. It's an alternating current. So if there's an alternating current, what that means is that it's going to produce a magnetic field on this iron core that would be north-south for one cycle, and then it's going to switch, and it's going to become south-north for the next cycle, and then it's going to switch and become north-south again. And so what's happening is, since I have a alternating current on the primary side, what I'm doing, what I'm doing is I am inducing a changing magnetic field in the iron core. Now that iron core is going to, there's another side to that iron core, so that means on this side over here I also have a north-south magnetic field that's changing within a coil of wire. So again, same idea, it's got to be alternating. And what that would do then is it would induce a current in that coil of wire on the secondary side. It's going to induce a current. And so this is what we call mutual induction. So we induce an AC voltage on the other side. That AC voltage is going to be of the exact same frequency. So the frequency at which it is oscillating on the left is going to produce the same frequency on the right. If it's 60 hertz, which is our standard AC oscillation frequency, the output will be at 60 hertz. A different voltage, though, depending upon the number of loops in each coil. So depending on how I arrange those coils, I can change that voltage either to step up or to step down. So I can either take the voltage on the primary side and make it be bigger, or I can make it be smaller based on the ratio of those terms. Now the equation is pretty simple. You'll see that the equation is not up on this board up here. And that's simply because this is the first time I've ever actually gotten to teaching Faraday's law. I think it's an important concept, we just never got to it. The ratio of the voltages are in the same ratio as the turns, number of turns. Now, can you guys tell that this one has a small turn and a large number of turns? This would take that voltage and it would step it up. It would make it be greater. If this were 100 turns, if this had 100 turns on that side, and this had 1,000 turns over here, and I can do that simply by just having a different number of turns on one side versus the other. That would step that voltage up by a factor of 10. It would be 10 times bigger. If I put in 120 volts here, you turn into 1,200 volts there. That's what a transformer does. So if you were watching the current wars, if you were able to watch that, when Edison asked his apprentice, he's like, hey, what's the voltage for an AC transmission line? He goes, 270,000 volts. That's how they did it, was just taking one side and then stepping it up to a much larger number of turns on that side to increase that voltage. That allowed them to transmit that much further than with DC. DC, they said it could run for a mile before they had to put a generator in. And this one, they're like, we could run it across the United States if you step that voltage up high enough. Okay, that's the idea. Now I'm going to show you, I made one of these things a while back so people could see what it would look like. So this is a very simple, very inefficient transformer. Made it from materials that you'd find at like Home Depot. So I just have some L brackets. Those L brackets are the iron core that allows me to sort of have the magnetic field intensified, because I can take the electrical current flowing through those wires and get the iron core of the L brackets to sort of intensify that. And you notice on one side I have 300 turns. I just took some turns around a PVC pipe so that I could take that out and change it. On the other side I have 150 turns, and that's of that magnet wire that goes around there. If I had it hooked up like so, and these are again the input leads, and these would be the output leads. So I might call this if this is the primary and that's the secondary, what kind of transformer is it? Step up or step down? It would be a step down. What would happen to the voltage if I applied 120 volts here on that side, AC? This voltage would be 60 volts. If I flip that around and I said, nope, I'm going to run it like this, now, and I had it coming in from the left, it would be a step up, and it would step it up by two times. Okay? That's the idea of a transformer. Okay. Now, I want to show you guys when you guys plug in your cell phone charger. You guys plug it into a wall outlet, correct? 120 volts. You are not going to apply 120 volt charging voltage to your cell phone. That would fry the component. So that little cube that you guys might have and things like all those little things, all they are inside of that is just a little transformer, and probably a series of diodes to take an alternating current and turn it into more of a direct current. That's okay. That we don't quite understand that yet. But a charger for a cell phone contains a transformer reduces 120 volt AC to 5 volts AC to charge a 3.7 volt battery. So your battery in your cell phone is about 3.7 volts. It also contains diodes. Don't worry about that. Suppose the secondary coil contains 30 turns and the charger supplies 700 milliamps. Calculate the number of turns in the primary, the current in the primary, and the power transformer. Okay, so I'm going to draw a little sketch for you. And I gave you guys some space for you to be able to do this as well. And so I've lost my pen to write on the board, so I can't do this very neatly. Here's the typical. Don't touch the screen with the paper. The typical drawing for a transformer looks like this. First, can you guys tell if this is a step up or a step down? It's going to step down, right? So I would have more turns on the primary than on the secondary. So this would be the primary, that'd be the secondary, this is the iron core. And so you might think of that as the drawing for the transformer. Okay? On this side, I'm connecting 120 volts. Got to be AC, because I need to have that magnetic field constantly changing on the primary side. And then on the secondary side, it's going to transform into about 5 volt. So over here, I'm going to get 5 volts AC on the output. Part A, I want to calculate the number of turns in the primary side. So this one they said N is equal to 30. And I want, so N on the secondary, this is N on the primary, and I want to determine what that value is. Okay? Now, if you want to, instead of having to memorize those equations, just realize that the voltage is in the same ratio as the turns. So let's just set up a simple proportion. I might say 120 volts AC is to N on the primary side. That's going to be in the same ratio as 5 volts AC is to N on the secondary side. They have to be the same ratio. Now, if I set up that ratio and I know NS, could I solve that for NP? It's pretty simple, right? Just proportional ratios there. So go ahead and just solve that for N sub P. and you should be able to get that the number of turns is, once you have it, turn tell that person next to next to. Are you guys calculating 720? Okay, so I would need to have 720 turns on the primary side to step that voltage down from 120 to 5. Okay? Questions? Okay, letter B. Calculate the current in the primary. Now, I want to take a moment and say that we are assuming, unless stated otherwise, that the transformer is 100% efficient. So let's assume (100% efficient), which is never going to be true, but a lot of these transformers are designed to be highly efficient. So usually what we do is we calculate these numbers based on 100% efficiency. Now, the key idea here is that power would be the same. We would say power on the primary would be equal to the power on the secondary. So we're not going to increase or decrease power. We're just going to transform the voltage. Now you guys might remember that power is I times V, right? So if I change the voltage, I'm going to change the amount of current. But the product of those would be the same. So I want to get, let's go ahead and write this out in equation form. I could say voltage on the primary multiplied by current on the primary is equal to voltage on the secondary multiplied by current on the secondary. Power is the product of voltage and current. So if I step the voltage down, I should make the current be higher. Okay. Now they're asking for what is the current on the primary. So solve that for ICP. Just the ratio of VS to VP multiplied by I in the secondary. So this would be 5 over 120 multiplied by I in the secondary, they said was 700 milliamps. So that would give me a current on the primary side of 29.2 milliamps. Okay. Last question on that one is, what's the power transform? I would like you to try that one. How much power is being transformed there? So I'm changing voltages, I'm changing currents, but what's the amount of power being transformed? Just take a moment so you can calculate that one. Once you have it, tell that person that you're sitting next to. I'm not hearing much, and it sounds like it's really quiet. So tell that person, come on. Take any one of those. You got the voltage, you got the current on both sides, so you just multiply them together. Come on. Okay, stop me when I get close. 1 watt, 2 watts, 3 watts, 4 watts, 5 watts. Come on, stop me. What is it? What'd you get?
3.5.
Say it out loud, my God, 3.5 watts. It's not that. Just take the current, multiply by the voltage,
That's
right?
what see how
It-
long.
Thank you. This is on recording, my gosh. All right. Take I times E. How did you calculate it, Jack? Did you take the primary voltage and the primary current?
Yeah.
That would be fine. Zane, did you do the secondary voltage and the secondary current? You could, because the power is the same on both sides. Okay? All right, our last, guys, we finally made it. It's our last slide for this unit. It is how the power companies use transformers to minimize energy loss and maximize, what do you think they're trying to maximize? Let's try. Oh, that's true, but that's not the term there. We're going to try to minimize energy loss, but maximize safety. So we are trying to make this a, guys, the reason why Edison lost the battle, and the reason why there was such a hoopla about, oh my gosh, Tesla's current's going to kill people, is because if you have 270,000 volts of potential, isn't that lethal? So they're like, wait a second, one of the things that sort of kept Tesla's alternating current from being out there in the beginning is because it's this is unsafe. But you can make the energy loss minimal and keep the safety maximum by changing where we step up that voltage. I want to take a moment, and I just want to look at what's a standard transmission setup for taking power from the power plant and running it to our homes. So the power plant is where we burn the coal, we run the steam through turbines, we turn magnets in the presence of coils of wire, and we produce a power, right? Electrical power. There's some step-up transformers. These transformers here are taking something from 12,000 volts of potential, stepping it up to 240,000 volts. So this transformer, you guys see these things, right? You see these things maybe outside, you see them in closed-in areas. Those are transformer stations that take the voltage from a one value to another value. Now they step them up to incredibly high voltages. They transmit the current at very high voltage. And then once we get to the point where we want to make it safe to operate in our homes, we step that back down. So we step it up to transmit at great distances. You guys notice, you guys see the breaks in the, well, that's not an earthquake, right? That's showing a break in the distance, right? So we can transmit this thing hundreds, thousands of miles if it's at really high voltage. Then we step it back down to go into our homes. Now, usually coming into our homes, this is a secondary substation where it takes it from 240,000 volts down to 2,400. Then we have some other little bucket transformers. Those are the ones that are on your telephone poles outside your home. They take it from the relatively small voltage, 2,400 volts, and takes it down to 240 to go into your home. So we are maximizing safety by having the voltage here be small, but we're minimizing energy loss by having the voltage really high. Now this all goes to this concept. You remember that power is equal to I times V, V squared over R, and I squared times R. This equation shows that the power loss in transmission wires is reduced by the square of that current. What that means is if I look at the power is equal to I squared times R, if I can make the current small, then I can make the energy loss in those wires small. So the idea here is to step that up so that I can get a really small current in those wires. Now the resistance is somewhat fixed. The resistance of those wires might be 0.4 ohms. To go from one side to the other, their conductor, actually mostly they're aluminum, but they have very little resistance. But when you send them out over hundreds, if not thousands of miles, that resistance will add up. If I run that at a low voltage, if I run it at 240 volts versus 24,000 volts, I'm going to lose a lot more energy in those wires. So I'd like to do a couple of quick calculations with you and see if you guys can do these as well. So here we have a 120 kilowatt power station sent to a small town from a power plant that's 10 kilometers away. Transmission lines have a total resistance of 0.4 ohms. Calculate the power loss if the power is transmitted at 240 and 24,000 volts. So first thing I'm going to ask you to do, can you calculate for me? I have to reset my screen here because I can't write on it. Can you determine the current that must be delivered to the home at 240 volts if they're going to have 120 kilowatts of power being delivered at a voltage of 240? Could you determine the amount of current that must go through those wires if I send that 240 volts? Take a moment so you can do that.
Power on. HDMI connected. Connecting. Connected.
If I were to transmit that power at 240 volts, the amount of current that I'd have to deliver in those wires would be 500 amperes. So if I transmitted that power at 240, I'd have to have 500 amperes of current flowing through those wires. Now, if power is equal to I squared times R, this would be power loss. This is what we would call dissipative heating, right? The wires are going to get hot. When I was floating the coil of wire around those magnetic fields, you're like, what? The wire gets hot. That's because the wires themselves will lose some energy in the resistance of those things. So the power loss would be that current squared multiplied by the resistance in those wires. So if I have 500 amperes that I'm running through those wires, and it's only 0.4 ohms of resistance, that's pretty small. But because that current is so large and I'm squaring it, that would be equivalent to about 100,000 watts that is lost. I'm only giving 120,000. So if I'm losing 100,000 of 120, I would say that now that's the loss of power. That means that I'm 83% lost. You guys agree that's very inefficient? I'm only retaining, what, 17% of the energy is useful. The other 83% is just lost. Now, what I'd ask you guys to do is do the exact same thing, but now transmit it at 240,000 or 24,000 volts. You guys do the same calculations there with pumping that voltage up to 24,000 compared to 240 volts. If I can pump that voltage up to 24,000 volts, I only have to deliver 5 amperes of current. And so now I have a trickle flow, which means that the power loss is going to be much smaller. That becomes 5 squared, not 500 squared. And the amount of power loss I get now is 10 watts lost. I'm transmitting 120,000 watts of power and I lose 10 watts. You think I can live with that? As a percentage, that would be 0.0083% lost. Now, when I compare these two, it's a no-brainer, right? They're like, we're going to transmit the voltage at really, really high values so that we can minimize energy loss. They're like, step up, step down, and that makes it safe. But that's the reason we do it. Make sense? There's about 5% of the people that are walking in our country that understand this. About 5%. There's very few people that understand. I wanted to make sure we got to that so you guys can see it. People are like, why are those things at 270,000 volts? They don't understand it. You guys do. It's to minimize energy loss. Okay? All right. Guys, I'm going to stop there. I have a couple of problems for you. Let me stop the video.